So here in this question, they're asking you for the ratio of magnetic moments of Fe3 and CO2. What is this? This is basically your Fe3 plus and this is your cobalt 2 plus, right? Okay, your options are given to you in the form of a ratio. So let's go ahead and find the ratio. So first thing that we will do is we will write down the elements. We will write down their ground state electronic configuration. Then we will write down the excited state electronic configuration that is expected out of us. Then in that excited state electronic configuration, we will find out the number of unpaired electrons, right? And from there, we'll be able to find out the magnetic moment. Okay, so let's get started. So first you have iron and then you have cobalt. What is the atomic number? So I hope you remember that iron is 26, cobalt is going to be 27, manganese, iron, cobalt, nickel, copper, zinc, right? So you have 26, 27. So let's write down the electronic configuration. Your inner electronic configuration is of argon. After that, what do you have? You have 3D, you have 4s. So first you fill 4s, write 4s2, and then you have 6 electrons left. So you will write 3d6, correct? What about Fe3 plus? Fe3 plus, basically you have 23 electrons. So write down argon, write down 4s 0, because first we always knock out the electron from the s orbital. So then you have one more electron to go, so that will go from here. So you have 3d5. Okay, great. Now you have cobalt, whose atomic number is 27. So you're going to write argon 3d7 4s2. Then you have to write the configuration for cobalt 2 plus. So that is going to be what? This is going to be 25 electrons. So write down argon 3d7 4s0, correct? All right, great. So now we have to find out the magnetic moment. How exactly do we find out the magnetic moment is the question here. Find out the number of unpaired electrons first. You can see in iron you have 3d5. So basically you draw your 3d orbitals like this. So you have 1, 2, 3, 4 and 5, and 1, 2, 3, 4, 5 electrons, which means you have 5 unpaired electrons. So what's going to be your magnetic moment? So you will have mu is equal to under root of n into n plus 2, right? What is n? N is your number of unpaired electrons. So this is going to be under root of 5 into 7, which is nothing but under root of 35 Bohr magneton. Cool. Similarly for cobalt 2 plus. So let's see, you have your d orbital like this, 1, 2, 3, 4, 5, right? These are your 5 d orbitals. So here you have 1, 2, 3, 4, 5, 6, 7, right? So how many unpaired electrons do you have? 3. So your mu here will become under root of unpaired electrons is 3. So 3 into 3 plus 2, which is 3 into 5, that is root 15 Bohr magneton. So what is the ratio of magnetic moments? It's going to be root 35 is to root 15. This is going to be your ratio as we have calculated. So the right answer here is going to be option B. Okay, so here they're asking you which of the following species is planar and non-polar with 2 lone pairs of electrons on the central atom. Wow, that's really specific, right? So they want it to be planar, they want it to be non-polar, and they want 2 lone pairs on the central atom. Okay, let's get started. So first you have option A ClF3, then you have option B XeF5 minus, option C PCl5, option D BrF5. Okay, so let's see. You have first of all option A ClF3. So option A ClF3, chlorine is of course going to be your central atom which has 7 electrons available for bonding, correct? So here you can see one is going with fluorine and the other 2 are also going with fluorine. So you have 4 electrons left out. Now, what is your steric number? Your number of bond pairs. So you have 3 bond pairs plus number of lone pairs. Then you have 2 lone pairs. Steric number is 5. So this is going to be sp3 dehybridized. Correct? Okay. So if it is sp3 dehybridized, then you would expect the shape. Sorry, you would expect the geometry to be what? You would expect it to be trigonal bipyramidal in geometry. But due to the presence of lone pairs, what happens? The shape that you actually see is going to be a T shape. Correct? So you have T shape here. Now let's see. So when you draw the structure of ClF3, you get this. Okay? You have lone pair here and here. Now see, due to the ClF bond, the bond moment is going to be towards F, here also, here also. Okay, so the summation of these two vectors will give you a null vector. Okay, this much I agree with. But then what about this vector? This bond moment due to this ClF bond is not getting cancelled out by anything, right? And then you have this bond moment or some sort of moment due to the lone pair, right? We have to account for that also. So here basically we're not going into the calculation, but your mu net is going to be not equal to 0. So where can we write that? We'll write here mu net is not equal to 0. Okay. Next, what do we have? We have XeF5 minus. Hold on. So what happens in the case of XeF5 minus? Let's see. You have option B, XeF5 minus. Interesting compound. You have xenon as your central atom here, which has 8 electrons available for bonding. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, you have this. Now you also have this negative charge to account for. So what we will do is we will go against our basic intuition. We'll place the 9th electron there on XeF5 minus. Seems really odd, but we have to do what we have to do, correct? So now you have your F5. So basically you have 1, 2, 3, 4 and 5. So you have 5 XeF bonds, okay? And then you have these two lone pairs. So your steric number is going to be number of bond pairs, which is 5, plus number of lone pairs, which is 2. So this is going to be 7. So with steric number 7, your hybridization is going to be sp3d3. Correct? It's going to be sp3d3. And what happens with steric number 7? What is the geometry that you're expecting? Okay, so generally the geometry that we expect is going to be pentagonal bipyramidal. Okay, so basically you will have a pentagon. You will have a pentagon as such, and you will have there will be a bond above and below the plane. It will look something like this. Okay, but here you have two lone pairs, right? So you have two lone pairs. So because of that, what happens is it's of course no longer going to be pentagonal bipyramidal. Instead, what happens is this: you have Xe, you have lone pair here, you have lone pair here. Okay, the other 5 spots are filled up by fluorine atoms, and you have a negative charge on this Xe. Okay, very interesting ion if you ask me. So what is the shape of this molecule, or sorry, what is the shape of this ion that we actually observe? So you can see that this is a pentagonal planar structure. Okay, this is going to be a pentagonal planar structure. Okay, now let's see. So in xenon and fluorine, which one is more electronegative? Definitely fluorine, right? So your bond moment is going to be towards fluorine in all the 5 bonds, correct? Now you have 5 vectors, each at an angle of 72 degrees with the other, right? Because this is a pentagon. Okay, so each at an angle of 72 degrees with the other, and you need to find out the resultant vector due to the vector addition of these 5 vectors. What will it be? Think about it, and I want you to think about it intuitively. Okay, so when you think about it, basically you will realize that all of these vectors will add up to a null vector or 0 vector. Okay, so here what happens is that your mu net comes out to be equal to 0. Okay, this is a planar structure. It has 2 lone pairs and the net dipole moment is 0, which means it is a non-polar structure. Fine. So this question had very high demands, but we did manage to find something that actually stood up to the standards. Fine. Next we have option C, PCl5. So I'll solve that here. Okay, option C, PCl5. This structure is pretty simple in front of the structure we just discussed, right? So here what do you have? You have phosphorus as a central atom. It has 5 electrons available for bonding, and all of them are gone with chlorine. Okay, so you basically have steric number is equal to 5. Hybridization is going to be sp3d. Correct? You have sp3d hybridization, which means the structure you would expect is going to be your TBP shape, right? TBP shape. Okay, and since you have 0 lone pairs, you will actually get a TBP shaped structure here. Okay, and the moment you understand, the moment you see that this is going to be a TBP shaped structure, you know that this is not going to be our answer. Why? Because now this is not a planar structure anymore, right? This is not a planar structure, so I don't care if it is a non-polar molecule. It doesn't have lone pairs, so that's also there, right? So this is not going to be our answer because this is non-planar, okay, and no lone pairs. Right, then we have option D, BRF5. So last thing, BRF5, here of course bromine is going to be the central atom. You have 7 electrons available on bromine, right? So it looks like this. Then you have 5 fluorine atoms which take away the electrons, 5 of them as such. Okay, then you have a lone pair. So what is your steric number going to be? Your steric number is going to be number of bond pairs, which is 5, plus number of lone pairs, which is 1. So this is going to be 6. So with the steric number 6, what is the hybridization that we get? We get sp3d2, right? And sp3d2 means what? Means it is going to be octahedral. One second, let me just clear things out here a little bit. Okay, so we have octahedral geometry is what we are expecting, okay? But due to the presence of a lone pair, what happens? Instead of octahedral geometry, what you get is going to be a square pyramidal structure, okay? It's going to be a square pyramidal structure, and here you will have the lone pair. Okay, so this is the plane, and this fluorine is basically above the plane. Cool. So yet again, this is a non-planar structure. It has only 1 lone pair, not 2 lone pairs. What about your net dipole moment? Even that is not equal to 0. Your mu net is equal to, sorry, your mu net is not equal to 0. So here you have mu net, sorry, here you have mu net is not equal to 0. It is, what? It has 1 lone pair, and it is a non-planar structure. So this is the farthest away from our answer, right? So we have checked all the options and we have only one option that's going to be a right answer. So option B, XeF5 minus, is going to be the right answer to this question. So here they're saying consider the following statements and arrange in the order of true or false as given in the codes. So you have statement 1, statement 2, statement 3. Depending on whether they're true or false, your answers will come out to be like this. Okay. So let's see. You have statement 1. This is saying Na2O2 is greater than, Na2O2 is less than MgO, is less than ZnO, is less than P4O10 in terms of acidic property. Fine. So what do we have here? First thing you need to know that here when they say acidic property, and mind you, we are talking about what? We are talking about the oxides, right? So acidic property of oxides is directly proportional to the non-metallic nature, or you can say this is inversely proportional to the metallic nature of element. Okay, metallic nature of element, correct? So here you have sodium, magnesium, zinc and phosphorus. You have these 4 things to compare, right? Now, what do we know? We know that definitely, right, without even looking too much into the periodic table, we know that phosphorus is a non-metal, right? Rest 3 of them are metallic in nature. We will compare their order, but phosphorus is a non-metal. This much we know, which means P4O10 is going to have the maximum acidic property, right? Now we have it between sodium, magnesium and zinc. So you have sodium here, you have magnesium here, and you have zinc somewhere here in the periodic table. Very roughly, you know, I'm estimating it. So what do we know? We know that as we move from left to right across a period, the metallic nature decreases. Okay, which means what? Which means that the acidic nature of its oxide will increase, right? So magnesium oxide is definitely going to be more acidic than Na2O2. This much we can say. Now, where do we factor in zinc? That is the question. All right. So, when you talk about metallic nature, this is known that sodium is greater than magnesium is greater than zinc. This is something that we know. Okay, this is a general trend that we have observed in, you know, all our years of study. Like from 9th, 10th standard, you have seen this. Okay, so here you have ZNO. Okay, so basically here you will have ZNO, then you will have Na2O2. Sorry, this is incorrect. My bad. So here you will have magnesium oxide, then you will have Na2O2. So Na2O2 is going to be the least and P4O10 is going to be the most in terms of acidic property. So let's see. Okay, this is what we had also proposed. Na2O2 is least, followed by magnesium oxide, followed by zinc oxide, followed by P4O10. Okay, so yes, this statement is indeed true. Cool? Fine. Next, what do we have? We have sodium, magnesium, aluminium and silicon in terms of their first ionization. So now what do we have? We have sodium, magnesium, aluminium, and then we have silicon, right? We are dealing with IE1. All right. So what do we have here? See, generally the trend that we expect is that as we move from left to right across a period, the ionization energy is going to increase. Correct? As you move from top to bottom in a group, your ionization energy decreases. So the expected trend is going to be sodium least, followed by magnesium, followed by aluminium, followed by silicon, right? Sodium least, followed by magnesium, followed by aluminium, followed by silicon. Okay, but here what they're suggesting is an anomaly, right? Here they're suggesting that magnesium is actually greater than aluminium. Okay, why is that so? It is so because magnesium, we know that magnesium is a group 2A element, right? So group 2A elements, they have NS2 as their outer shell configuration. Okay, so NS2 is a fully filled subshell. Okay, now from here, when you want to remove one electron, you are going to disturb a very stable electronic configuration, which is why second A group elements have considerably higher first ionization energy than their group 13 counterparts, right? This is important and this is true. The order that they have suggested is indeed true. Remember it. Next, what do we have? Now we are talking about electron affinity. Fluorine greater than chlorine greater than bromine. Okay, so electron affinity, what is it? Electron affinity is basically more of a qualitative term. Okay, when you are going to introduce an electron into a neutral isolated gaseous atom, what is its tendency to accept the electron? I am not talking about it numerically. I am just saying which is going to be more likely to accept the electron. So higher the likeliness of being able to accept the electron, higher is going to be the electron affinity. In terms of numerical values, we talk about electron gain enthalpy. That's a different thing. Here we're talking about the tendency. So that's electron affinity. So here you have fluorine, chlorine and bromine, right? So this is the same group. These are your halogens. So as you go down the group, the general trend is that your electron affinity decreases. As you move from left to right in a period, electron affinity increases. Okay, what does it mean? It means that in a given period, your halogens are going to be the ones that are most likely to accept an electron. But ma'am, shouldn't that be noble gases? Because noble gases are the rightmost, correct? Noble gases are not going to be a part of this discussion because noble gases already have their NS2-NP6 configuration. So they are not interested in accepting or donating any electrons at all, right? So this discussion is limited only up to group 70. Fine. So in a given period, your halogens are going to be the ones which have maximum tendency to accept electrons, right? Or which will have the highest electron affinity. Great. Now what about it in terms of fluorine, chlorine and bromine? In terms of fluorine, chlorine and bromine, as you go down the group, the electron affinity is supposed to decrease, which means fluorine should have the maximum, followed by chlorine, followed by bromine. Correct? This is what we would expect. But of course, there's a catch here, right? So what happens here is that chlorine has a higher electron affinity than fluorine, and this is because fluorine is very small, right? Fluorine is the most electronegative element. I hope you remember that, right? It's a really small atom and it has 9 electrons, right? And then you're trying to add another electron to it. So what happens is this incoming electron faces a lot of repulsions, right? It faces a lot of intra-atomic repulsions, inter-electronic repulsions, because of which what happens is fluorine has a lower electron affinity value than chlorine, or fluorine has a lower tendency to accept electron as opposed to chlorine, right? So here what are we saying? We are saying that chlorine is the element that has more electron affinity than fluorine. And if you come to think about it, this should have been obvious, because there are two things you're expected to remember when we talk about the periodic table. First is that fluorine is the most electronegative element, and chlorine is the one element which has maximum electron affinity. So definitely whatever else you put in front of chlorine, chlorine will be the one that has higher electron affinity. So this one unfortunately is false. Okay, so now we've discussed all of these three trends, and it's going to look like true, true, false. That's the answer we're going for: true, true, and false. And that's here in option C. So option C, true, true, false, is going to be the right answer to this question. Okay, so here they're saying what will be the oxidation number of the underlined element in CrO2Cl2. Okay, and what is the underlined element here? Chromium. Okay, so you have CrO2Cl2, and here you need to find out the oxidation number of chromium basically. So let's get started. Let's say that chromium has an oxidation number of X. So you have CrO2Cl2, this has an oxidation number of X. Oxygen will have -2, chlorine will have -1. So now let's write down the equation and solve for X. So you have X plus 2, that is the number of oxygens, multiplied by the oxidation state of each oxygen. That's going to be -2, plus 2 into oxidation state of each chlorine. This is going to be -1. This is equal to 0. What does it mean? It means X minus 4 minus 2 is equal to 0. So you have X is equal to plus 6, correct? And plus 6 is here in option B. So option B, plus 6, is going to be the oxidation state of chromium, and it's going to be the right answer to this question. Alright, so here they're saying what will be the oxidation state of hydrogen in H2S and LiH respectively. Okay, so here you have H2S first case and you have LiH, right? Why are they asking us about oxidation state of hydrogen? Hydrogen will just take +1, right, everywhere. Why are they asking us about this? What's so special? See, so the thing is, hydrogen has the capability to take +1 or -1, right? It has one electron, it has 1s1 as the configuration. It can donate that one electron and take a +1 charge, or it can gain one electron and take a -1 charge. These two things can happen. Be very careful. Okay, so how do we decide whether it is accepting an electron or donating an electron, whether it is taking on -1 or +1? That depends on which element it is attached to. So if it is attached to a more electronegative element, then hydrogen will act as if it has the oxidation state of +1, right? And if it is attached to a less electronegative element, then it will take the electron from that lesser electronegative element and behave as if it has oxidation state of -1. These are the two cases. So now let's see. First case, you have H2S. So here you have hydrogen whose electronegativity is around 2.1 and sulfur whose electronegativity is 2.6. Okay, so you can see that sulfur is more electronegative than hydrogen, because of which what happens? Hydrogen here will take on a +1 oxidation state. Okay, so this is sorted. What about LiH, lithium hydride? Here this is a very important example of what we call a metallic hydride or a saline hydride or a salt-like hydride. Okay, so here what happens is you have LiH, so this breaks off as Li plus and H minus. Lithium hydride, and the moment you hear hydride, much like halide, you know that it is X minus. So hydride is going to be H minus. Here hydrogen takes on -1, right? Okay, so respectively in H2S and LiH is going to be +1 and -1, which means option A +1 and -1 is going to be the right answer to this question.